Hi, welcome to Procedural Content Generation using Computational Intelligence. I'm Dr. Joseph Alexander Brown, speaking to you from Minneapolis University. To begin with our discussion of computational intelligence and procedural content generation, I think we should start out with the idea of what is procedural content generation. Julian Tegelius defined in 2011 that procedural content generation in games refers to the automatic creation of game content via algorithms. Ian Parberry said that the automatic creation of video game content, where content means anything that would traditionally be done by a human designer. We want to look at, for example, the idea of creativity versus scut work, where scut work is the stuff that is hard, that we don't want to do, that we can rely on an algorithm in order to create, and we want to deal with creativity. How does this get placed within our game space? And we want to give the designer more ideas for creativity. In both of these definitions, we see the idea of creation is not done via a designer, but done via an algorithm. The designer is placing this into the system in order to create the creativity of how should this thing be designed, much like an architect versus a builder. The roots of current PCG can be traced back as early as the 17 to 1800s with Prussian Kriegspiel, or wargaming. And generals would actually sit down and create these board games in order to test various troop deployments. And as you can see here from this early example of a Kriegspiel board, we have already the beginnings of this n-by-n grid of squares with differing train types. There is even an ability for players to roll up terrain randomly or pseudo-randomly in order to figure out where certain terrains would go and create a new play space that they could work with. So this idea of movable elements in games is not exactly new. Looking at common day board games such as Zombies or Carcassonne, we also see examples of movable board elements. And this kind of gets into what we're doing in terms of placing designs inside of level design using evolutionary computation. So PCG researchers like to make a lot of claims that it's necessary to make good games, that it speeds up development process, that it allows for a unique game experience, creates new content that a human couldn't make, extends replay value, and meets with user requirements for the game space. Now, the only problem is a lot of these claims have some very large holes in them. And that is, it's not exactly necessary that I use PCG inside of it. There's lots of good games that don't use these techniques. It's not as fast or cheap as people like to put it. It actually costs more development time because I now have to build a generator in order to build this, and I need specialists in order to do it. It doesn't create always unique game content because, well, if a computer can design it, then a human probably could have just designed the thing if we're looking at a level design. Human content is often way better as well because there's a lot more kind of testing upon it, and we can do a lot of very fine detail work. Repeatability in some instances actually suffers in that we have repetitive quests and randomness inside of it. The problem with, is this level even actually complete, and how does it fit in with the game's narrative? And some user needs are not met by the content, whether the game is too easy, too hard, or too annoying. So the question is, why use procedural content generation? Well, the big thing is that it's not always the best design tool, depending upon that. For large AAA developers, where you have lots and lots of people on a development team, you can afford to throw more people at the problem. But let's take a look at some of the indie designs that use this. Let's look at what those pieces are that do have this. Independent games usually deal with a much smaller staff. They require more content to be produced per hour of work. And they need games usually with also swift time to minimal viable product to be released. They have simpler game mechanics, which leads to a simpler content space and less critical code areas. And they're also willing to invest not just in the product itself, but also in their own development as programmers. Looking at where does procedural content generation appear in these sorts of games? Look at The Binding of Isaac, in which you have random elements inside of this roguelike development. Faster Than Light, another one with this roguelike space. Spelunky, again, we see this kind of roguelike element of constant respawning and random level generation. But look at even bigger ones like Minecraft, where the world seed is developed via a procedural content generation for that world space. So we see that when you have a smaller development team, you require something that can take over for that. And usually it would be better spent time to take that effort in terms of hours and put it into the development of a larger world space. So I would like to say that PCG is something where we need to focus on what's the strength of it. That it's not a magic bullet. It cannot be relied on to make the entire game, but it's a really good force multiplier when it's used. The time spent using a PCG generator needs to make a content which is going to be of a high quality. And maybe we built it into a roguelike mechanic, but we have a gameplay mechanic that meets with that. PCG is not going to excuse poor design choices or bad designs. It's a tool, and the designer needs to apply that tool in the ways that it's most effective. Now, in terms of where do computational intelligence ideas fit into this, and in terms of designing the level? Well, this is where we need to look at how do we define a good level. So in terms of this, we've defined kind of the process now kind of mechanically, but what's the goals of the generator in the end? So we can see the goals of a generator, and this is coming from, again, work by Tilebased, that we should have speed, reliability, controllability, expressivity and diversity, creativity, and believability. So for speed, we need to create game content on time for the user experience. So if this is a loading screen and we're developing a new level, or is this we need to do it offline and build the game beforehand? In terms of reliability, we need to ensure that whatever content we generate is going to meet with the base requirements of the game without breaking mechanics. If I have a level without an exit inside of a dungeon, that's going to be an impossible level to play. It needs to prevent against that. And we have to work that into how we define what a good level is. Controllability is the next issue, and we have to look at it in terms of meeting with what a human designer would do via an algorithmic method. So if I'm looking at creating a dungeon that's suitable for a certain player that has 5 enemies that can be faced by a level 10 wizard or a level 4 barbarian, I have to prove that somehow. And that becomes also, how do I develop a good evaluator for a dungeon? Expressivity and diversity. So the generated asset should not look really different from what a human might create in this game, and we also want to have a number of different but equally relevant pieces of content. This becomes, again, very hard to measure. How close is this? In terms of expressibility, we want to have a nice big search space that we can move through. And we don't want to create the same dungeon over and over again. Creativity and believability becomes the next issue. And when we talk about this we're really looking at a Turing test. We're trying to show that this is, again, not any different than one produced by a designer. Again, very hard to measure objectively. Now, in terms of believability, we also need to look at what type of world are we doing in terms of the art design in that. If I'm creating a small little village and I put a church inside of there and I put a graveyard in there, well, the graveyard should probably be close to a church. Oh, well, that's something that we can check algorithmically and check. Is that church close to a graveyard if we have one? And ensure that that is held. We wouldn't have just a random shack in the middle of nowhere unless there was maybe some road going into it. Or it's necessary in terms of the dynamic of the game. Maybe this is a hermit that lives out there. So we need something in order to ensure that. Okay, so in terms of that, we have a spectrum of needs in terms of different games as well. A flight simulator is going to need some form of low detail areas, whereas something more like a Skyrim or a Fallout is going to have something more detailed in terms of it. First-person shooters, we need to look into maybe how do we have sight lines? How does the player move through that space? In terms of a real-time strategy game, we need to look at how do units move over that space? How do we deal with that sort of moving? Okay, so let's take a look at one example of level design out of my own work in terms of dungeon creation. And let's take a look at some previous examples. So here is kind of the Zelda overworld area here. And you can see it has these kind of cave-like blocked out structures, getting close back to that look of that German Kriegspiel. Pokemon has this same sort of flow through the overworld and the spaces inside of it, of how a player moves through that space. If we look at this game, for example, this is Half-Life 2. Half-Life 2 we can also see as being this sort of cave-moving space. Skyrim also has these units. Let's go back to Kriegspiel. Kriegspiel has these block units inside of it, and this tile-based simulation. Here's Carcassonne, a board game that has to do with city generation, and again, we see these tile units on it. So in 2012, we started working on an idea of, could we evolve dungeon crawler levels with some sort of relative placement of tiles? And the reason why we want to start with tiles is it was close to the current big games at the time, and one of them being Diablo-like games. And that this is actually one of the methodologies that Diablo uses, but doesn't have the same amount of checks upon it. And we can see here that Diablo has these sorts of squared tile units already. So in terms of creating that, we can see this image here with all of those pieces that made up that previous image of all of the different dungeon tiles that were generated in order to make that. And looking at Jay Wilson in an interview with GameSpy, he was looking at how they do this sort of generation, and he said it takes actually a lot more effort to build something that's constantly random in terms of it, that you need more pieces inside of it, and you require more and more assets in order to make up for making this feel of randomness or developing different gameplay spaces. So you can place other tokens, you can place all sorts of different other units on top of that. So the tile size also has another aspect, and that's the gameplay decision here. So we can see that dependent upon how we place our tiles, it also makes changes in terms of how the power sets work. So tile-based placement is already being used inside of the industry, and we wanted to look at that. And we're looking at how do they currently do it. And the idea of their algorithm was basically you create a set of tiles with a number of connections or walls, so doors in terms of this. And while the map is not large enough, select a random tile, place it into one of the free connection points, and if no connection point exists, then and I'm not big enough, then start over. So really what it's doing is just doing a growth out of that. And these larger game elements can create a bunch of different level generations inside of that. So let's take a look at the control that a developer has on this very simple algorithm. We can bias the generator a little bit, like probability to either cap out a place or increase connections. And we may want to increase connections early and then close it off later. And it can be shifted throughout the generation. So we can have some sort of probability to increase caps. In terms of expression, it creates very nice, tight little areas. Tiles are commonly square, but we can work for spaces with other sorts of arrangements in terms of the placement. And the connections are a little bit less regulated. We don't just have a linear path through a system, and we can even have a few cycles. Now, how do we look in terms of this for story and gameplay? Well, we can force the generator explicitly place some form of encounters or treasure in more logical areas of the space. So early rooms are more likely to be open, later rooms are more likely to bottleneck. At the end of these late rooms, we put bosses and treasures and stuff that we can grab. So incorporation of story elements can also be put in this because you can say, I want to have this many rooms up until the boss. So we already have a relatively expressive generator, but look at all that randomness. So why would we want to get away from that? Well, I want more control. I want the ability to say what a good level is through that. And this is where computational intelligence is used. This is where we want to start looking at something like genetic programming. So what is genetic programming? A genetic program is a population of tree-like representations of solutions to a problem which we'll use the word chromosomes for. This is kind of a cartoony version of biology that we're going to be looking at. And these chromosomes can be manipulated via crossover and mutation operators. Each chromosome is going to be assigned some form of fitness score based on its ability to solve the problem. In this case, we can say, this level is better than this level. It meets with more of our requirements for what a good level is. So as long as we have some form of definition of ranking between levels, I can assign some form of fitness score. Chromosomes with a high fitness are selected to continue on to the next generation with a higher likelihood. So it's a fitness-biased generation. Not based, but biased. So this process is repeated until some threshold of time is reached. So if we're looking at, you have a loading screen and you need to generate whatever you can in 30 seconds, then we can look at that. Or a chromosome has a specific level of fitness So the evolutionary approach allows us to have some form of stochasticity, some randomness inside of the generation. It allows us to search through space via population, and it allows for the map structure to be defined in a very flexible way in terms of this tree structure. It's a discrete search space that I can now look through. I can look at the population of all possible levels. So the goal is to create some form of powerful and flexible map generation algorithm that produces maps that can be easily converted into playable game levels. And we want to work within what the game developers are already using in terms of their methodology, which is these tile set generators. We want to, basically speak to them in certain terms of their own language and then build this in. We want to encapsulate this desired structure then into how we evaluate what is this fitness function. So challenges in terms of building this fitness function is that we have these sorts of collisions between rooms. The tiles are sometimes inflexible and hard to fit inside of that, and we want to ensure some form of connectivity. This is a rather big search space, and we need to then define what is a good level. So in terms of our representation of this, we're looking at a tree in terms of this. And each tree has a tile associated with that. Child nodes are going to be placed in a relative positioning to their parent based on what doors they have inside of us. The tiles have two parameters. One is the number of doors that the tile has, and the other one is what is the structure of the tile being placed. These door slots are where you're going to join on the next child. Child nodes are connected to their parent nodes at the next available door of their parent, and placement can also cause doors to become unusable via blocking via walls. Also, a null tile is added to allow doors to be blocked and skipped. This might be that, we don't want to go over in that direction first. We want to look at something else in terms of the relative positioning. So it allows us to block that off. Or we're getting to the end of our generator and we want to just block off those doors. The tree is traversed in a breadth-first fashion to increase stability. If we look at a depth-first search, we would get one single path out of that first node. However, we're interested more in creating these highly connected groups of rooms, so we're going to look at all the possible children. Nodes that cannot be placed are also going to be skipped and removed from the chromosome. This is in order to do a removal of the amount of bloat that you get inside of genetic programming trees, where extra bits of tree that are unusable or have no effect on the solution get carried on to other generations, and your size of the representation gets larger and larger and larger. Mutation operators do single changes to the chromosome. We have defined 3 different mutation operators. The first one selects 3 nodes with 1 or more doors available and adds child nodes to them. The next is a trim that selects a leaf node and changes it to a null if it isn't already, or removes it otherwise. And the last is change, which selects 2 random rooms and changes what room tile is on top of them. Crossover takes 2 different parents and combines them with each other. For this, we're going to first take a copy of the 2 parents, select a random subtree in each copy, and exchange those pieces across. This allows for groups of rooms to be moved to different locations on the map. And sadly, this results in a little bit of symmetry in our final map structure. So crossover into GP tree, for this example, we have our 2 trees. We're going to select which branch we're going to swap. We select our 2 swap points, make the actual swap, and there you can see the final product has a little bit of each of the previous trees. For our selection operator, in order to decide who gets to breed, we randomly separate the population into 120 groups of 4 chromosomes each. We sort each of the groups by this fitness, how good are they as a level, and replace the 2 least fit chromosomes in each group with the children of the other 2. This leads to how do we actually define this fitness model? And this guides the search towards maps comprised of small, tightly packed clusters of rooms that are connected to each other via an efficient series of hallway nodes. There's a strong preference for maps that contain up to 3 special rooms that are placed near the perimeter of the map. These are our boss challenges, these are our treasure rooms. Tiles can be separated into 3 different categories: the event rooms, which are our big boss fights, the normal rooms, and hallways. Each category is going to be treated a little bit differently. Event rooms offer a very high reward for the first 3, as long as they're placed a minimum distance from the origin. However, in the event that we place more than 3, we're going to basically say that that level is incorrect, that we put too many bosses, too many battles into this level, and we're going to say that the entire level has a fitness of 0. Normal rooms are rewarded if they're connected to both hallway rooms and to non-hallway rooms. So I want to have tight packs of rooms, but I also want to encourage some amount of hallways in that. Hallway rooms have a small penalty every time they're placed, so I don't want random hallways being generated. But if hallway rooms are connected to non-hallway rooms, to either event or actual rooms, they gain a bonus that overtakes that. And they get an additional bonus up to 5 different rooms that are connected. So as long as our hallway is actually connecting rooms, the fitness will increase. But if we just place random bits of hallway going in all directions, it'll actually decrease the fitness of that. And so what have we defined in terms of our level? We want 3 event rooms, that we want highly connected areas of rooms, and that we want small hallways that connect a few different rooms. And as you can see here, we end up with that in terms of our level structure. You can see where these rooms have been put together such that I get highly connected components of rooms with hallways moving between them and our 3 event rooms. Now notice also something very odd here. Even though we used a tree representation, we have cycles inside of our groups. And you would think that with a tree representation we wouldn't see cycles. Well, this is the fun bit. Remember how I said that there was doorways and that they could be placed? Well, if a doorway lines up with another doorway, we treat that as a passable door in terms of it. However, if the doorway lines up with the wall, we block off that doorway. So even though we haven't expressly said we can have cycles, it will build those into it based on our current fitness function. Let's take a look at what happens when we change some of the fitness. This one here has been told, don't generate more than 100 rooms. And you can see we end up with something that is nice and compact, and is actually probably pretty likely to be seen in Skyrim or Fallout. Here we've said that each of the event rooms should be placed as far away from as possible in terms of a path distance from all the other event rooms. And look at what we have. We have groups of hallways that have basically led to 3 separated components from the original start location. Here we've said that we want to have some amount of rooms past some big event. So this would be, I need to defeat the boss before I can go on to the next part of the level. And you can see that it's done that. Now, this leads to some strange local optimums though. As you can see in this example, that it wasn't able to grow anything off of the event room. Also remember how I said that when you do these tree cuts that you end up with similar connected components? This one already has those as well. You can see here that these 2 sections are rather similar in their approach of how they solve for that area, and it's probably having to do with using that sort of operation. So there's 2 big things that I would say that these experiments taught us. The one is that your representation, how you define the data structure, defines some of the structure of the map. In terms of, we used genetic programming, which led to these sorts of similarities in areas. If we just did nothing but mutation, we removed the crossover operation, I would expect it to not show this sort of similarity. Is this good to have this similarity? Maybe. It depends upon what our narrative and what our art design is. This might be beneficial. It might not be. But we can change that via the representation. Secondly, you can see that by changing the fitness function, we end up with a different generation of what a map looks like. And this is very helpful. This is what we want to do, is have something where via changing how we organize parameters, we can come up with different levels. So where does this lead us beyond just level generation too? Where does this lead in terms of other areas of procedural content generation? Let's take a look at architecture. Could we procedurally content generate that? Could we create different architectures and use it for that? Sure. Could we use this for placement of units inside of a factory? Well, it's the same sort of problem. All of these have these sorts of connections between them. So how do we move from level generation into something more serious? It's rather simple. We just look at these pieces in a different light. We change what our fitness function is for it. So architecture is probably the easiest way that I can say that this sort of level generation could be useful to anyone outside the field of games. You can see also a lot of designs in terms of music, in terms of poetry, in terms of story and narrative, in terms of textile design. So this is the sort of area that procedural content generation moves into. And what it is it's a force multiplier. It allows us to not just define exactly what we want, to spend the time doing the designs to get exactly what we want. If we don't have exactly what we want, but we have a good idea, and we can say, I want this more than that, then we can start to build generators that will move towards it. And this is why computational intelligence is extremely valuable in terms of procedural content generation, and an area that will be growing inside of the future. So I'd like to thank you very much for listening to this talk,